All right, folks, good afternoon and welcome to BayOne's Technical Bootcamp. Today is Tuesday, October 13th, and we have a very interesting session lined up in front of you. And before we get started, I just want to go ahead and start sharing my screen. Sandeep, if you can let me know if you can see my screen.
Yes, Suva, I'm able to see your screen.
Wonderful, wonderful. And again, welcome to the BayOne Technical Bootcamp. For those of you who are our regular attendees, thank you again for your patronage. We truly appreciate it. And as you know, this is a way for us at BayOne to give back to the community. And we have been championing diversity, inclusion, equity, and women in technology initiatives. And we've been running several boot camps, including cohort sessions, dedicated cohort sessions, especially before the COVID crisis. We had sessions last year. And many of you who were our regular attendees at that time and got your data science certification through us continue to patronize these boot camps. So we truly appreciate and please keep returning back, spread the word. We would be glad. So what you see on the screen is our team, and we are committed to your success. So thanks to all the attendees, and also a big thank you to all our presenters, like Sandeep we have on the call today. It is because of you that we are able to give back to the community. So thank you all for joining our session. So with that being said, very briefly, these Bay 101 tech boot camps, as we call them, 101 because these are fairly elementary concepts, but we cover all kinds of digital technologies, of course, starting with software development, including big data, IoT, and cloud computing, DevOps, and also AI and machine learning. For those of you who attended last month's AI chatbot session, I assume you would have liked it as well. And if there is feedback in terms of what kind of sessions you want to attend, please let us know. The best way to get in touch with us is by sending an email to bootcamp@bay101 at bay1.com. I'll share the email ID in a second. So these are the different kinds of events we conduct, and they are for different kinds of audience, but it's mainly the sessions are open and it's free. The company sponsors all these events, so we definitely would like to see you in large numbers. Tuesday sessions run from 4 to 5:30 p.m., 90 minutes, as you can see. And usually we have an industry SME, or if not an in-house SME or myself hosting these sessions. Do mark your calendars in advance. We usually have sessions every Tuesday. The last few weeks have been off and on due to several reasons. But if you want to know more, you can always send an email to bootcamp@bay1.com. Zoom links to minimize Zoom bombing and issues such as those. We try to generate a different link for every meeting, as in this one. So for those of you who have received an invite directly from me, be reassured you will be getting these invites going forward. For those of you who have been forwarded the invite, please send a note to Bootcamp so that we add you to our mailing list. That way you don't have to rely on somebody else to get the invite forwarded, okay? So I'll just pause here for a second. Any questions regarding who we are, what we do, and what these boot camps are all about? All right. So for now, we have a limited offer. I know many of you are engineers eager to sort of transition into your new job or actively interviewing for different positions. It was always good to have your skills up to date, polished, right, and be ready for that next technical interview. And Sandeep very shortly is going to talk about some very interesting dynamic programming concepts to sort of give you some idea of how these conversations need to be structured, right? So if you want to get a flavor of how recent technical interviews happen, and if you would want to participate, we are offering free, no strings attached, mock interview opportunities. So if any of you is interested, now these are for software development, front end, back end, full stack, automation, even technical project management kind of positions, if you're interested in any of that and would like to spend maybe half an hour to 45 minutes with us to undergo a mock interview kind of evaluation, we would be glad to do that, provided there is availability. So this is first come, first serve. If you're interested, send an email to bootcamp@bayone.com. And I know some of you on the call are already participating in this program, so thank you for that. So we hope to give you at least some challenging questions and help you prepare better for any upcoming interviews. Okay. So any questions on this? Just remember, when you reach out, do mention your details, attach your resume, and also mention your target job profile, whether you are looking for a software developer, if it is whichever. You don't need to mention the name of the company, but you can mention whether it's a FANG type company or whatever industry it is. So that way our SMEs are able to tune the interviews better, so that it helps you sort of prepare in the process. Yeah. All right. The email ID is bootcamp@bayone.com. So both for registration as well as for the mock interview request, you can send an email to the same email ID. Okay, and why is preparation important? I show this slide every single meeting. I know it's kind of boring, but look at that. Unless you are really, really prepared, if you're 1 out of 50, the chances of succeeding in your first attempt at interviews is going to be very slim, okay? So you got to prepare yourself. It's relatively easy to prepare your day-to-day activities, right? What you do in terms of your technology stack and probably even the language syntax if you're a Java programmer, whatever. But then what happens in interviews is they don't talk a lot about what you do. Instead, they talk about the fundamentals, right? They ask you questions on CS basics, data structures, algorithms, and so on and so forth. So with that being said, the session today is a continuation of where we left off a few weeks ago. If you may remember, Sandeep Ayloo had joined us for a couple of sessions. Today probably is his third session with us. He had talked about several things. And in the last session, he talked particularly about recursion, about complexity of time and space, and discussed a couple of lead code problems on recursion, right? So today he'll briefly recap that and discuss some of the challenges that traditional recursive approaches to programming creates and how one should go about addressing those challenges. Now, most of you would have heard of the term dynamic programming, and some of you probably even know that and even practice things like, tabulation and memoization and so on and so forth. But we'll hear from Sandeep holistically, and he'll dive deep into these things. And folks who are relatively new to programming, I had made a request. I'd also shared the link to our previous recording on recursion. So I presume you have all done your homework. You have your recursion stuff all brushed up and ready to go. So without further ado, Sandeep, I'd like to welcome you to the forum. Good afternoon and welcome.
Thanks, Suva. Good afternoon, everybody. Could you give me the host permission to share, Suva?
Absolutely, Sandeep. I'm actually doing that right now. And while we transfer the guard to Sandeep, any questions, anybody, regarding these boot camps in general or about today's session? So Sandeep, you have the co-host privileges, so feel free to start sharing your screen.
Yeah.
Over to you.
Okay, sure. Let me. So are you guys able to see my screen?
Yes, we are able to see your screen, and the session is also being recorded.
So good afternoon, everybody. My name is Sandeep Ayloo, and I work at Thales Security as a senior software engineer. So today's topic is about dynamic programming. So in dynamic programming, we have two sorts of approach. One is top-down approach and a bottom-up approach. And before we go to dynamic programming, let's talk about, I'll give a brief introduction to recursion. I've already done a detailed discussion on recursion last time. So I'll just touch upon recursion, and then I'll talk about a computer science concept called memoization. It's just a concept. and then how it is used in dynamic programming, why it is used in dynamic programming, memoization, and then the different strategies in which you can implement the idea of dynamic programming. So this is all the discussion would be about. So let's get started. So recursion, right? So recursion is just a mathematical idea. And a simple explanation for recursion is a function calling itself till it accomplishes something. And every time a function calls itself, there is a change in the input. And because this function will be calling itself, and this, like, for example, you have function n is calling function n-1, and function n-1 will be calling n-2. So for every recursive calls, there needs to be a break condition, because eventually this function calling itself should stop, right, at some point, and that is defined by the break condition. So every recursion has the following template. You have a break condition, then you have a local computation that you do in your function, and then you pass on the other rest of the computation to your recursive calls. So this is all about recursion, and this is just a programming construct. This is just a pseudocode. Now let's talk about the important aspect of computer science is memoization. What is memoization? So memoization is just an idea. The idea here is when you are computing something, you pass input to the function, right? You pass input to the function and you compute it. But if you're passing the same input to the same function and recomputing the same thing again and again, there is actually wastage of resources that you're doing, because you have already computed certain aspect using a particular function and you're redoing the same operation again. So the idea here was, what the computer scientists have thought was, if you're actually doing the same thing again and again, why don't we persist in some place and we can later on use it whenever we want to do it. So what's the advantage of that? So what is the advantage if we actually persist data and reuse it instead of recomputing it from scratch? So let's take a small example here and let's see what happens when we have the memoization being implemented and when we don't have memoization not being implemented. So memoization is a computer science term, and it's etymologically, it sounds very similar to memorization, but it's just a term that computer scientists have invented. And so we will call it as memoization. Now let's just for a moment, let's imagine you have a function f of x, and the time required for computing f of x is one time unit. The time unit could be millisecond, second, anything. But the time required to save or retrieve this value f of x from a persistent storage is 0.1 time unit. So I have this thing where, where I have a function, you pass some input to it, and the time taken for computation is 1 time unit. Once you have the value, to persist it and retrieve it from a persistent storage or any non-persistent storage also, doesn't matter, but you have some storage, and that time unit is 0.1 time unit. Now let's look at a pseudocode. My pseudocode here is compute f of 1, that is the first line of code that I have. Then I have compute f of 1 plus f of 2. Then there's another third line of pseudocode is compute f of 1 plus f of 2 plus f of 3. Now, how much time does f of 1 takes? So I've already mentioned that f of x will take 1 time unit. So obviously compute f of 1 will take 1 time unit. Now when the compiler goes to the next step, it hits this line f of 1 plus f of 2. When it is executing this particular computation statement, it will take 2 time units, because you have 2 f of x, right? One with x equal to 1 and the other one with x equal to 2. So the total time is 2 time units. Now the compiler will go to the next, next statement. And here we have f of 1 plus f of 2 plus f of 3. So the total time that would be taken to compute this particular statement is 3 time units. Now what is the total execution time? It is 1 plus 2 plus 3, that is 6 time units, which is okay, not bad. But let's try to do the same thing with memoization and see how much difference we will get. So I did a small modification to my code. Instead of compute f of 1, I have written compute and save f of 1. How much time this will take? 1 unit for computation and 0.1 unit for saving the data in some storage. It could be a persistent storage, it could be a volatile storage, it could be a non-persistent storage, but in some sort of storage, it is taking 0.1 time unit. So the total time that it has taken right now is 1.1 time unit. Now the next step, what I did was get f of 1 if exists, else you compute and save. What I'm that line, that particular syntax, what it says is, if you have f of 1, you just get it, or else you compute and save it. Similarly, for f of 2 is a brand new computation, right? We haven't touched f of 2 so far. So that's why f of 2 has just compute and save. Now, what did I say? Time required to get is 0.1. So to get f of 1, the time required is 0.1. And to compute f of 2, the time is required is 1 time unit. And to save f of 2 is again 1.1. So the total time required for f of 1 plus f of 2 with memoization is 1.2 time unit. Now let's go to the third statement. Even here we have get if exist, else compute and save f of 1. Similarly, get if exist, else compute and save f of 2, plus compute and save f of 3. Because f of 3 is a brand new computation, so there is no checking there. So you just compute and save it. But f of 1 and f of 2 are old computation or previously computed, but you're just making sure that you just check in the storage. If f of 1 is there, then you get it, or else you compute and save. Similarly, the same thing holds good for f of 2. If it is there in the storage, you get it, or else you compute and save. Now, how much time does it has taken? For f of 1, it is 0.1, f of 2, it is 0.1, but for f of 3, it is 1 time unit for computation, and for saving, it is another 0.1. So total time required is 1.3 time units. Now you compute the total execution time. It is 3.6 time units. So you might say, okay, it's just, it's just like, I got like 40% benefit, like 3.6, just more than half. But this is just a very basic, it's very simple code, right? Now imagine you are doing a computation on a knowledge graph of size of that of Google's data. Then if you have millions of nodes, and instead of computing million operations, you just do 500K operations, that is a significant amount of time that you save, right? With memoization. So you see, as the size of the data increases, even though this is a small strategy, but it gives such a significant impact in the computation time. So that is why this memoization is just a technique. It's just an idea. The idea is when you're recomputing, when you're reusing the same computation, you might as well save it and retrieve it rather than just doing it again and again and again. So that you save time, you save resources, and you have some other benefits, like your CPU will be less strained and all other stuff. But the bottom line or the most fundamental benefit that you get is the time required to compute the operation will get significantly reduced. So this is the idea of memoization. So let's, and now the next slides will talk about how can we utilize or how can we take this idea and implement in dynamic programming. Let's go to the next slide. So dynamic programming is just a technique. It is just a technique to find the optimal solution. But how do you find the optimal solution for a given problem? What you do is you divide the problem into subproblems, and then you find the optimal solution for each subproblem. That is just a technique. So dynamic programming is just a paradigm. It's just a concept. It's just an algorithmic technique. What you do is you find the optimal solution by dividing the problems into subproblems, and then you get the optimal solution for each subproblem. So if you have a huge, like for example, let's go to some other layman terms. Like for example, you have a garden. And now you, instead of, like if you have to work on your entire garden, you divide it into subtasks. smaller tasks, and you efficiently do each and every small task, and you put together these efficiently performed tasks together so that you can get the end result. So this might sound similar to that of a divide and conquer strategy, but the thing is, here we are trying to find the optimal solution, right? So there's a slight difference, but it still falls under the paradigm of divide and conquer. But the difference here is you're trying to find the optimal solution, and the optimal solution is equivalent to the optimal solution of each and every subproblem. That is the idea behind dynamic programming. And there's nothing much to talk about that idea, but the actual idea will kick in when we do this sample problem that I'm shown here. Now imagine this is a graph or some sort of cities or something like that. Each node is like a city or a place, and there is a user, or there's some person who is traveling from city A to city D, and he wants to check what is the longest path. Now let's go with so now the problem here is there is some person, he's just traveling from A to D, and he wants to find out the longest path from A to D. That is his problem, and that he's trying to do it for whatever reason. Now let's do it in a non-dynamic programming way. So imagine if this guy is standing here and he just wants to find out the longest path. And just imagine for a moment that this guy doesn't have any idea about dynamic programming, and he's just using his common sense to travel from A to D. So what does common sense dictates? When you have to do longest or something shortest, what we do as humans, we go with a greedy strategy, right? We take the best option that is available, right? So what this guy would do is, the guy who's standing here, he would use his common sense, and greedily he would just go from A to B2 because it's showing 10, because now he has 3 options, B1, B2, B3, and he would take the best option that he has and he will go to B2. And that's perfect, right? Because he's seeing only 3 options and is taking the best option. But once he lands at B2, he has only one option to go to C, that is 1, and he will take this route, B2 to C, 1. Now when he's at C, then he has 2 options, C to H or C to D directly, but C to H cost is 1 and C to D cost is 3. So he will take C to D. Now what is the total cost that this person has incurred is only 14 units. But if you look at the graph, but if you have a complete picture, a 3-dimensional view of this entire city graph, then you know that this guy has done a mistake. So initially he should have taken 2, and then he should have taken 1,000, and then he should have taken 3. Then that would have given him the longest view. So this is the difference. When you're looking greedily at this problem, you just take the immediate available option and you move forward, the immediate available best option. But if you look at it 3-dimensionally from a top view, you would see that, oh, he actually missed this route, B1 to C. And this idea of taking something that is available immediately, the best option, is called a greedy strategy in computer science. And it's a technique, but it is used for a different set of problems. But when you have to do something with optimization, or when you have to do with overall computation, then greedy strategy will not work. Even in life, it doesn't work, right? When you, like, for example, you're trying to achieve something, and if you just look at the immediate benefits, then you never know, you might lose something in the future. So it's the same technique that we have here. So this is a pseudocode for greedy strategy. What the user has done is, he has just taken the max of AB1, AB2, AB3. So he has taken the max of these 3. And then which is ABX. That means it could be B1, B2, B3. Then from ABX, he has taken a max of BXC. So in this case, our BX is B2. And then he has taken the max of B2C. And there is only one route, one path, and one cost, that is 1. And then he has taken ABX plus max of BXC plus max of CD. From C, from C to D, what is the best option? And the best option that he had is 3. Now, what are the outputs? AB2, AB2 plus B2C, AB2 plus B2C plus CD. And the total cost is 14 units. But unfortunately, that is not the right answer because that is not the most optimal thing. So this has failed here. The greedy strategy has failed. But what we need to do, if this is failing, then we need to think about a different strategy, right? So that strategy is you take all possible combinations and then you evaluate what is the best option. Because now if you do greedily, if you just take one option, it is failing. So what we need to do is you need to look at all the possible options, all the possible routes, and retrieve the maximum path from A to D. Then you can, then then it promises that at least we know that there is a chance that we can get the right answer. And that's where dynamic programming kicks in. So what we need to do here is, because now we are evaluating all possible options from our start point to end point, what we will do is we will divide this problem into subtasks. And then we will evaluate the best possible optimum solution for each subtask. And then we'll sum it up and then we'll give it back to the user saying that, hey, from A to D, the maximum path is this much. So you guys have any question till here why non-dynamic programming way fails? I can answer, or else I'll move forward, because moving forward, it becomes more and more involved. I can take like for a minute, I can just take some questions if anybody has any questions.
Sandeep, I have a question. Are you able to hear me?
Yeah, I'm able to hear you. Go ahead.
Yeah. So can all the recursion problems can be solved using dynamic programming? Am I like?
Okay. So what is dynamic? So recursion is a programming construct. Anything that you can do recursively can also be done using for loops iteratively, right? So recursion is just a idea. It's just an idea to write code, right? Anything that you put in recursion can also be put in iteratively, right? So that has nothing to do with dynamic programming. Dynamic programming is an idea. So you have a problem, and the problem is you have to find the optimal. It's an optimization problem, right? So if you have to do optimization, then you have to consider all the options. And that is where dynamic programming kicks in. Recursion or iteration is just a convenience in which you want to write the code. And I have actually discussed this thoroughly in my previous session, where I specifically mentioned when to use recursion, when to use for loop. A dynamic programming problem can also be done iteratively and also recursively, but it all depends on the comfort and the flexibility that the developer has and the ease of writing the code. So please do not mix recursion with dynamic programming. Recursion is just a technique to write a code, but you can also write iteratively. You can use iteration and implement dynamic programming. You can use recursion and do dynamic programming. But you will understand why recursion is so much used in dynamic programming in my next example, where I talk about the idea, why recursion, memoization, they go hand in hand with all the dynamic programming questions. But that will give you the answer, okay? Does that answer your question, or you still have some confusion here and there?
No, I think I got the point. Thanks.
Okay. So let's go to the, so what are the possible paths? So now if you're having a three-dimensional view of this city or this particular graph, or a top view of this graph, that you know that there are three possible paths, right? A, B, 1, C, D, that is the one max path. Then you have A, B, 2, C, D, that is another max path. And then you have A, B, 3, C, D. So basically you have three paths that are potential candidates to be the maximum path. And among these three, the green path is the best path, right? Because you have something called the B1C cost is 1,000. So A, B1, C, D is the most promising answer for our city graph that we have here. Now let's try to solve this problem in a dynamic programming paradigm, okay? So what we are trying to do, we are trying to find the longest path from A to D. Now, what are the candidates that you now, as I already told you, that we cannot go with the greedy strategy. So we need to consider all the options and we need to move forward. So if I'm standing at A, what all options, if imagine there's some person who's standing at A and he's looking at three possible routes. Either he can go to B1 or he can go to B2 or he can go to B3. So the potential candidates are AB1 plus the distance from B1 to D, AB2 plus the distance from B2 to D, AB3 plus the distance from B3 to D. And among these three, he needs to take the maximum. Previously, what we were doing, we were just considering the max between AB1, AB2, and AB3. But that was not giving us a solution. Instead, what we need to do here is, we are evaluating all possible options. Now, what I'm saying is, okay, give me the path from AB1 plus the maximum path from B1 to D, comma, the other candidate would be AB2 plus the maximum path from B to D, AB3 plus the maximum path from B3 to D. So if you see here, I'm not just taking AB1, AB2, AB3. What I'm saying is I will evaluate all possible options and I will consider all of them. So the first option that I have is AB1 plus the maximum path from B1 to D, right? Then the other option that I have is I'll go to B2 and from B2 I'll get the maximum path till my end destination D. Then the third path that I have is AB3 plus the maximum path from B3 to D. And among these three, I will find the maximum. Now, what is max B1 of D? So this, I think this stuff is clear, I believe. Now, what is max B1 comma D? Now, B1 comma D is, what is the maximum path from B1 to D? Is B1C plus max of CD, B1C plus max of CD, comma, the two possible paths, right? B1C plus max of CD or B1E plus max of ED. So there are two paths, B1E, the path from B1 to D is, you have two options. B1E, he can take a path route from B1E and reach D. He can take B1C and reach D. So max B1 comma D is max of, you take both the paths and you take the maximum. And that's what I've done. So from B1D, you have B1C plus maximum of CD, C to D, B1E and maximum path from E to D. That's what I've written. Similarly, for max B to D is the maximum path that you can get from B to D is max of B to C, B to C plus max of CD. And on top of that, you do a max. Similarly, you have max B3D. The maximum path from B3D is B3F plus maximum path from F to D. Or you have another path is B3C plus maximum of CD. And between these two, I'll take the maximum path. Between B3C and B3F, I'll take the maximum path. But inherently, if you see here, there is some sort of recursion that is taking place. You see how here the max function is calling itself, but in a different, with a different inputs. You see here, max, AB1, AB2, AB3 paths, but for AB1, and I'm again computing max of B1D. So the function max is calling itself with different inputs. So you are observing some sort of that paradigm is kicking in when we are implementing the dynamic programming technique here of considering all the options. We are seeing that intuitively, and we are also feeling that there's some sort of recursion that is taking place. That is the first observation, right? The second observation here is we are doing recomputation again and again and again. What is the one computation that we're doing again and again and again is max C comma D, max C comma D, and max C comma D. So we are doing it thrice. That is our second observation. But let's put it aside. Now, what is max C comma D is? Max C comma D is, you have two ways. One is you can traverse from CH, or you can directly go to CD. And between these two, you have to take the maximum. So max of CD comma CH plus maximum of HD. And between these two, you need to take the maximum. That is max CD. So this computation, the number 5, is being done thrice. And when you're doing the same computation again and again and again, you might as well store it in some kind of a storage and retrieve it, right? Because why do you want to do the same computation again and again and again, right? So these are the two observations. When we went with a sample, when we were trying to use this dynamic programming strategy, we observed that most of the problems, when you do it in dynamic programming way, they have that recursive nature to the problem itself. And there is some sort of recomputation that we are doing it again and again. So because we are doing recomputation again and again, we can leverage the technique of memoization. And how do we leverage it? That's a different story. That's implementation of it. But the idea is there is some sort of recomputation. Let's put those things in our back of our mind, and we will move forward. Then we can naturally understand why this whole recursion and memoization are being discussed so much with dynamic programming. And then once we do this computation, you have the green path is 1005. That is AB1 plus max B1D. You have red path, that is 14 units, that is AB2 plus max B2D. And then you have blue path, that is AB3 plus max B3D, that is 12 units. Now, between these three, you have to take the maximum, and that is 1005 units. And the total is 1005 units. So anybody has any questions, I will stop here for 2 minutes. If you guys have any question, please ask me here. And then we can talk about because this is the meat of the discussion. If you guys really understood this part, the rest all of them is you can logically develop on top of that. But if this part is kind of, there's some sort of noise or confusion, then better to clarify it right away. So please ask me any question at this point, anything, any kind of question, please ask me right now. I'll give 2 minutes, please ask me here. If you don't have any questions, then just let me know, I'll move forward. Okay, I think nobody has any questions, so I'll move forward. Okay, fine. I think nobody has any questions here, but I think I believe that you guys have understood like why we are doing, how when we try to divide our problem into sub-problems and try to do an optimization of the sub-problem, what we see is it has some recursive nature to it, and the computations are getting repeated. So these are the two observations that we have found so far. So that's what I've written. The previous problem gives us two insights. One is most of the dynamic problems are recursive in nature. And secondly, we can always speed up the computation, the processing time, or the result execution, or the execution of the result by using the technique of memoization, because you can always memoize it, right? You can persist it somewhere and retrieve it, right? So we can always do that. That is one way. But what is the second way of doing it? So this is good, actually. You know, I'm writing a function called max, and I'm passing parameters to it, and that function is calling its some other function and trying to retrieve the result. But here there is a concept. What we are doing is we are passing something to the input, and we are getting something to the something from the output, and accordingly we are trying to get the data. But what if I store all the combinations in the memory directly? Like instead of me using a function here like max, what if I just put if I just put all the values in my memory directly, like I'm not calling any max function, I will just put everything in the memory. Doesn't matter whether it's a max or min. I will put all the values in my memory, all possible values in my memory, and then I'll get the max of it. Even that is a strategy, right? What is a brute force strategy? Like if someone has to do a brute force, he will do, like if he's not sure which path is the longest, he will take all the possible values and he will put it in a piece of paper, and then he will just take the maximum one, right? That is another strategy. Here, I have done in a little bit more of mathematical term, little bit more of a programming way, where you have a max function, you pass inputs, and then that will call itself with a different sort of inputs. So instead of that, I might as well store all the combinations in the memory and just retrieve the maximum path value directly. Both are fine, right? One is you write a function, you pass values to it, and then you do a subsequent computation, or you just put all the values in the memory and just retrieve the maximum path value directly. Both are the ways in which you can get the value. So what is dynamic programming? So what we can understand, what are the insights that you can get here is, in dynamic programming, you can use recursion, or you can use recursion with memoization, or you can just use you can just put all the values in the memory and retrieve the maximum path value directly. In either of the three ways, you are getting the optimal result for your problem, which you were expecting from the problem, right? From the city graph, you were expecting the optimal path or the longest path, whatever, you're getting the answer. So either you can use recursion, or if you want to really speed up your recursion, you want to do recursion with memoization. Or if you are not even interested in doing recursion, if you think, man, I really don't want to do recursion, why do I need to go, do recursion? I might as well just put all my values in the memory and I'll just get the maximum value, which is also fine. That is fine, because ultimately what you want the maximum value, and you will get it in that way if you put all the values in the memory and just retrieve it. So these are the few insights that we found out while we were using the dynamic programming paradigm in solving a particular problem. Now let's carry these insights and let's take a problem and let's try to do it, okay? Now, before we go, I talked about memoization, right? How do you, so you might say, Sandeep, this is pretty good. You're asking me to persist the already computed data, but how do I do it, right? How do I do it? That is a question, right? As a developers or computer science engineers, we need to know how do you put it in the world of computers, right? So there are two ways in which you can actually achieve memoization. One is using hash map or a map. Another one is using arrays. Now, why arrays? Let's talk about it. So why do we need a hash map? Or a map for that matter? Because a map basically is nothing but a key value. And what is the key here? The key here is the max C comma D, right? And the value is the actual maximum path from C to D. So it makes sense, right? For this particular input, that is the output. So for this particular key, that is the value. So it is intuitively, you can put it in map. It is fair enough, right? I can say that, yeah, max C comma D, I can put it in a map as a memory strategy. But what about this arrays? Also, what about this arrays? So I also said here that we can store all the combinations in the memory and just retrieve the maximum path value directly. How do you put it in memory? If you want to put everything in memory, what is a memory? Memory is nothing but an array of cells, right? So even here, another technique where you can actually persist your data is using arrays. And in the world of dynamic programming, this idea of using arrays to persist or store your data is called tabulation. And how do you store it? If it's an array, it's like a matrix, because arrays can be a one-dimensional array or a two-dimensional array. But if you take it from a programming construct, then that becomes a matrix. And if it is a matrix, then you have a row and a column. And now here, what is the maximum of C comma D here? Is 3, right? And how do you store it in array? You will have, for the row C, the column D, you will store the value as 3. And that is how you store it. So whenever we use a hash map technique as memoization, we call it as memoization in dynamic programming. But when we use arrays, we call it as tabulation. So ideally, you can do memoization from a pure computer science perspective. You can put it in a map or an array. But in the world of dynamic programming, this first technique is called as hash map. The first technique is called as memoization. And the second technique is known as tabulation. So in an interview or when you're talking to any algorithmic expert, and where we say that, hey, what is your, what strategy are you using for DP dynamic programming? Then if you say memoization, that means you're using a hash map. But if they ask, no, I'm just using a tabulation, that means you're using an array kind of a storage as your memory. Okay, so please remember this thing. Memoization means hash map or map in dynamic programming. Tabulation means arrays in dynamic programming. Okay, this is how you save data in memory. Now we also discovered how to save data in memory. Now let's go to the implementation of dynamic programming. Okay, you guys have any question here or before I move forward? Can I get some response? Yes, no, or because it's like.
Yes, Sandeep, you can proceed.
It's pretty clear, Sandeep. We are able to understand.
Okay, thanks.
Questions here.
Okay. Now, what are the different ways of coding dynamic programming? So there are two ways in which you can go with dynamic programming. If you're using a map-based memoization, then if you're using a hash map plus recursion, if you're using a recursion and a hash map or a map-based memoization, then that is called top-down approach. But if you're just putting all the values in memory, which is an array, then also called tabulation, then that approach is called bottom-up approach. So somebody asked me that is all dynamic programming problems are recursion? The answer is no. It depends on what approach you're taking. And it just so happened that when you're using a hash map, the problem is evolving to be in recursive in nature. So we take recursion and we just move forward. But if you think that you don't want to go with recursion and you just want to put all the values in your memory directly and just retrieve it, then that is a bottom-up approach. Why the term bottom-up approach? Why the term top-down approach? I'll talk about it later. But for now, just put this idea in your mind that top-down approach means it is a recursion plus map as a memory, and bottom-up approaches you're using an array, also known as tabulation in the world of dynamic programming. These are the two things that we need to remember. And which approach to take, which approach not to take, we'll talk about it later. Now let's solve the problem, the same problem, because we said, right, this is recursion plus map-based memoization, right? So let's solve the same problem using a top-down approach. Now, what is in this? So I've just written like in this approach, we will use recursion to solve the problem, and anything we are recomputing again and again, we'll store it in a map and retrieve them as and when required. And what is a problem? You have a city graph and you want to find the maximum path from A to D. That is a problem. Now let's go to the pseudocode first. So here, what I'm doing, basically what I'm doing is, if I'm standing at this node, what are my neighboring nodes or what are my child nodes? I have 3 child nodes. So I consider all of them, and from there, I calculate the maximum from my child node to the end destination. Similarly, for my second child node, I consider it, and from B2 till the end destination, I compute the max. My third child node, B3 plus max of B3D. That is how my recursion is, right? That is how I'm doing, right? So let's put it in programming. What I've written here is, this is my start node. I'm getting the children. I'm getting all the children. In this case, it is, if my start node is A, I'm getting B1, B2, B3, and I'm putting it in a list. And for every child, what I'm doing is, and by the way, this is without memoization. So I'm not using any memoization. It's still a top-down approach because I'm still using a recursion. It is still a top-down approach, but this is without memoization. There is no memory. I'm not persisting my values at all. So what I'm doing here is, for every node, for every child, I'm calculating a temporary distance, which is the distance between my starting node and child node, plus get long distance from my child to end. And then what I do is, I have created a temporary variable long distance, and I'm calculating the math.max temp comma long distance. And I'm returning the long distance. The same thing, I haven't done anything extra. I have just put this pseudocode or this mathematical statements into programmatic syntax. And this is more of a Java kind of a syntax. But if you see here, one thing, so this get long distance, and this is a recursion code, right? So as I already told you, this thing can be stored in memory, right? So that's what I've written. Get long distance child comma end can be stored for future retrieval. But for now, we are not storing it, but this is without memoization. And this strategy of you take a child and you move forward is called depth first search strategy in graph traversal. So basically, so I'm doing a small segue here. In graphs, there are two ways of traversing a graphs. One is using breadth first and depth first. And this strategy where you consider each child and move forward, that strategy is called a depth first search strategy. And if you guys have any questions about that, I would recommend you to go and just read that thing, depth first or breadth first. But the strategy that I am using here right now is depth first strategy. Now, this is a code that doesn't have any memoization, but what did I say? I said that I'm doing this computation, right? Get long distance. So this is a potential candidate for storing it, for persisting in memory. So let's see, how do you implement the code with memoization? What did I already mentioned that it is a map-based memoization, right? So what I'm doing is map. What is the key here? The key here is get long distance with child comma end. That would be the key, right? So map get long distance x comma y, and the value would be the maximum distance. That would be our map, right? Now what I'm doing is, for every child node, I am saying distance between my start node and child node plus long distance. But what is this long distance is? I'm checking from this child node till the end if this data already present in the map. If it is present, you retrieve it. Check in the memory and retrieve it. But if it is not present in the memory, then you just go ahead and compute it. Else, if it is present, you get it. If it's not there, then what you have to, if you don't have something, you go and compute it, right? So you compute it, get long distance, child comma end, and then you persist in the memory. Because why? You might need it in the future, right? You never know. So that's why I'm putting it in my memory. So I am computing it here, get long distance child comma end, and then I'm persisting it in my memory. And then once I have my temporary distance, I'm checking it against my long distance value placeholder. What is the max? And accordingly, I'm returning it. This is a basic recursive code. But the one thing that you need to understand here is, in any sort of memoization technique, one approach is most people, I don't know how different people write code differently. Different people think about code in a different way. But especially if you're using recursion with dynamic programming, first write the basic recursion code without memoization, so that first you know what computations you're doing. This has been my strategy. Then you put some placeholder for the memory, and you just write a basic recursion code like this. I haven't put any. I know that this would be a potential candidate for memory, but I haven't written it. Once you have the basic recursive code, then you add the memory aspect to it, so that now it becomes very easy and simpler. But if you directly combine recursion with memoization, then it would become, it will take some time. It will take some time before you can directly put it. But if you're just beginning with dynamic programming, then I strongly recommend that you first try a top-down approach without memoization, and then you add the memory aspect to it. But before you add it, first identify which fields can be put in memory. What is the one that I can put it in memory? In here, I can put the get long distance child comma end, because that would be used again and again and again. Okay. And this is a top-down approach with memoization. Do you guys have any question here? Okay. So if you guys don't have any question, now let's go to the another approach called bottom-up approach. So this is top-down approach, which is fine, right? You start at the top of the problem, and then you go like you start at the top of the problem, and then you go deep down to the end of the problem. You do a computation, and then you move to the top again, right? That's why you're starting from the top, right? You're just assuming your distance between the start node and the child, and then you are moving forward. So you start at the top and you go all the way down. And that's why the term top down. Then what is bottom up? You start at the end and you move all the way to the up. It's like one strategy, you start at the top and you go down. And the other strategy is you start at the bottom and you build your solution on top of that. But in case of top down, if you start at the top, then you will go recursion with map-based memoization. But with bottom up, where you start at the bottom and you build your solution all the way to the top, that strategy is called array-based tabulation. And the idea here is you start at the bottom, at the at the minimum, at the lowest point, and from there you build up your solution. Now let's talk about it, bottom-up approach. So that is the idea, right? Bottom-up approach or tabulation. Now let's demonstrate the same thing with the problem. Now you have a sample problem here. The problem here is, I've actually discussed a similar problem in my recursion. I will not be going into the nitty-gritty details of this problem, but the idea behind this discussion is to make sure that you guys get the gist behind the bottom-up or tabulation approach of solving this problem. Okay, so the idea here is you have n steps, and at a time you can take 1 step or 2 steps. So find the total possible ways of climbing to the top. That is a problem. Now, how would you solve it? Let's imagine you have 4 steps, right? Then what are the ways that which you can climb to the top? The first way is you can take 1 step all the time. That is one way of doing it. The other way is you can take 2 steps here like this. And then once you reach to the 3rd step, you can only take 1 step, right? Because you only have 4th. But if you take 1 step, then you can take 2 steps again, then you reach 4. So total number of ways is 3 here. This is a problem. And let's assume we have n steps, and f of n and be the total ways to climb n steps. Now, as I already mentioned, there are 2 ways in which we can climb the steps. Either take 1 step or take 2 steps. And what did I have written here is, therefore the total number of ways to climb to the top is, you take 1 step, which is, and then when you take 1 step, how many steps are available for you? n-1 steps, right? So you take 1 step, and from there, you count the number of ways to reach top. That is n-1 plus, or, right? Because you can take 1 step or 2 steps, or you take 2 steps and you count the number of ways you can reach to the top. So f of n-1 plus f of n-2. Why plus? Because either I can take 1 or n-2, but if the problem says you should take 1 and 2 steps, then it should be f of n-1 into f of n-2. This is simple logic. If it's or, then it is always an addition, and you take f of n-1, you take 1 step, then what's the count? It is n-1, right? So the number of ways to reach to the top is, now you have to count the number of ways to reach to the top when the steps are n-1. But if you take 2 steps, then how many ways you can reach to top is n minus 2. And the total is n minus 1 plus n minus 2. And do you guys observe something here? We have the same thing, function calling itself with a different input. So there is some sort of recursion to this problem. That's okay. It's still a problem, and we just found out like that it has recursion. It has some recursion to it, but that's fine. So let's write the, by the way, this is not a tabulation approach. This is just a recursion. I haven't gone to the tabulation part. This is still the recursion. So count total ways to n is count total ways n minus 1 plus count total ways to n minus 2. And the function is calling itself. Now n minus 1 will call itself, n minus 2 1 will call itself. And eventually we need to have a break condition. What is a break condition? So the break condition is when you reach at the end. And when can you reach end? So if you have reached the 0th step, that means if you have reached the 0th step, then you have one way, right? If you have reached to the 0th step, then there is a way, right? That is give the count as 1. But if you have, but you cannot go beyond 0, right? But how do you put that in a mathematical way? Is if n less than 0, return 0, because you're subtracting here, and there could be a chance that this condition can go negative. So if it goes negative, then you return 0. That's it. As simple as that. There's nothing much to it. But the thing is, you need to understand what we are doing here. This is a recursive code. Now, how do you, so recursion always has to be visualized, right? Only then then you can get a complete gist of it. Let's visualize it. Pictorial representation of call stack. You have f of 3 here, and then you have f of 1, f of 2. F of 1 is calling f of 0, f of minus 1, but f of minus 1, you don't have any, this is not a valid path. So it will return 0, this will return 1, f of 2, f of 1. So f of 2 will return f of 1. This is 0, 1 path, f of 1, 1 path, f of minus 1, 0. This is a pictorial representation of call stack, and it is in the form of a tree here. And this is a representation of all the paths. You have 3 paths, that's what it shows here. So yeah. So now that we talked about this pictorial representation of the paths, now what we can do, the further thing is how this idea relates to tabulation. So that is a question, right? How does this idea relates to tabulation? Let's go here. So here, this is the function, this is a mathematical equation that needs to be satisfied while the problem is being solved, right? If you leave recursion aside, just think from a computer science perspective, this is the equation that needs to be solved. F of n is equal to f of n minus 1 plus f of n minus 2, right? So, and I already know that if n equal to 0, the answer is 1. And if n is equal to, like, let's see what are the break conditions that I have written. Yeah, okay. I just modified the break condition here. I've just modified the break condition. But if you have already reached the first step, step 1, or if you have reached the last step, that is a step 1, you start from nth step and you have reached the first step, which is our last step. Then how many ways you can climb that step is only one way here. And if you have reached the 0th step, then if there are 0 steps, then obviously you can climb it only in 0 ways, right? If there's 0 steps. But if there's only 1 step, then you can only climb it in 1 way. So these are my break conditions, right? And this is a linear equation. Now, this equation, what it tells us is nothing but from, also called as state transition. That is from the state of having n steps, how you can move to different state of having n minus 1 to n minus 2, right? This equation, this is a linear equation, and I can put all my values in the memory by using this small linear equation because it's so simple, right? So how can I use it? I already know the number of ways in which I can go to 0 steps are 0. The number of ways in which I can go to 1 step is 1. Then the number of ways in which I can go to 2 steps is 0 plus 1, right? Because when I'm at the step 2, I can only take 1 step, right? I cannot take 0 steps here, right? But when I'm at step 3 is again f of n minus 1 plus f of n minus 2. What is f of n minus 1, which is 2? That is 1. F of n minus 2 is 1. So if you have 3 steps, the total ways in which you can climb to step 1 is 2. If you want to climb to step 1. Now, what about if you're on 4th step, the total number of ways in which you can climb is f of n minus 1 plus f of n minus 2, that is 1 plus 2, that is 3, and so on and so forth till n. And the total number of ways in which you can climb n steps is again f of n minus 1 plus f of n minus 2. You already have those values computed here in this, in this array, and you can just retrieve it. But here, I didn't use any recursion. I'm just filling up all the values in the memory. So what we need to understand here is, if the state transition or if the subproblem has a simple mathematical equation, then we really don't need to go with recursion and using top-down approach. You might as well put all the values in the memory and just get the answer directly. But you can only do it if the equation is as simple, as innocent as this equation, f of n minus 1 plus f of n minus 2. If the equation is this simple, where the state transition is shown in a very simplistic terms, then you can use this bottom-up approach by filling up all the values in my array. And why did I use a one-dimensional array? Because you only have one variable, n, right? But if you have n and m, or x comma y, then you would use a two-dimensional array. So the idea that we need to remember here is, when you're doing a state transition, which you will be doing in dynamic programming problems, when the state transition equation is very simple, like this, where there's only one variable or two variables, then you better to go with a tabulation approach to a recursion. Why? Because recursion takes more time and more space, and also call stack space. And there's always a possibility of stack overflow. But in case of this, if the state transition equation is very simple like this, and so it's so simple, innocent, and it's so easy, then you might as well just put all the values in an array and just retrieve the maximum value. And let's see the code for it. Let's start solving the problem using for loop. Why did I use a for loop? Because it's an iterative strategy, right? I just need to fill all the values here. So I started with for loop. I initialized my array here, my memory. I had the break condition 0 and 1, and then I started filling it out, and f of I equal to I minus 1 plus I minus 2, and then I just returned f of n. So simple. There's nothing much. But the thing is, what is more important is you need to identify how your state transitions are related to each other. How are you moving from how you're moving from one subproblem to another subproblem. Once you have that equation, and it is very simple, if the equation is very simple, then you go with the bottom up with tabulation. But in this case, here the equation, you see the state transition is AB1 plus max B1 of D. This becomes very complicated. Like the state transition here has, a lot of child, and you need to compute all the possible combinations, putting them in memory. It becomes challenging. I'm not saying it is impossible. I am saying it becomes challenging. And as a developer, and if you're a lazy developer, then you want to make sure that you write minimum code with maximum output. Especially, and in data structures and algorithms, you have to write code in such a way that you take minimum effort. The code is written so elegantly and efficiently that it takes minimum effort to compute it and also read the code, right? So, but I'm not saying that this cannot be done in bottom-up approach. It can be done, but it becomes a little bit complicated. Then you need to have a memory array, two-dimensional array like this: A, B1, B2, B3, C, D, and A, B1, B2, B3, C, D, and then you have to fill it up. Then you write, God knows how many for loops you might have to put it. Then you have to put max value. Like, it becomes headache. And if you're an efficient developer, most of the efficient developers are kind of lazy. So they always try to they want to minimize their effort as well. So they just go with a recursive solution, and you just write it down in recursion, and the code becomes this. It becomes as elegant and as simple like this. So this is the difference between top-down and bottom-up approach. Now let's talk about the differences, top-down. And by the way, I said that why do we call it as bottom-up approach, right? So what are we doing in bottom-up approach? We are starting with the break condition, or we are starting with the known values. What are the known values? The known values are the break condition, and these are the values where the state transition will eventually hit. So that's why the term is, we go with the bottommost values, and on top of that you build it. But in top down is you go with the topmost problem, and eventually you go to the bottom or to the break condition, you'll compute, and then you'll move forward. So this is the bottom-up approach and top-down, and let's talk about the differences. So this, I have pulled it from Geeks for Geeks. The source is Geeks for Geeks. I was looking for an easy differences, and the only website that I found it was Geeks for Geeks. So you can also, guys, can look at Geeks for deeper understanding. But I have taken this particular this difference from Geeks for Geeks. So I'm mentioning the source as well. So what are we doing is tabulation versus memoization. Please remember, memoization in the world of DP is considered to be map-based approach, okay? Tabulation. So this is very important differences. We need to have this in our mind, because if you're in an interview context, now let's take dynamic programmings are mostly talked in interview context. Like the one question the interviewer always asks is, why don't you use tabulation? Yeah, why don't we use tabulation, right? Then you need to tell the interviewer that, hey, this is the problem with tabulation, and that's why I'm not going with it. Or sometimes the interviewer might ask that, okay, why don't you implement tabulation? Then, like, you know, the interviewer always wants to see your depth of understanding and your breadth of understanding, right? So if we have this differences, then it becomes really easy for us to tell and talk and navigate in any interview context, or even while doing any sort of algorithmic research or something like that. So tabulation. So here the memoization is state transition relation is easy to think. Yeah, it is easy because most of them are recursion in nature. So you can easily think. But here the state transition relation is difficult to think. So what he meant is, if in our problem, like the graph problem, the state transition, if you want to put it in a tabulation problem, it becomes, God knows how many for loops you're going to put, and how much complication you need to add. The same thing he has written. Code gets complicated when a lot of conditions are required. Code is easy and less complicated. So because it's also given, we already saw that when you're using the recursion, how simple the code has become, and it's very easy to read. But if you're using a tabulation, then so many for loops, if you have this for loop, then what is a max condition? If you have that for loop, what is a max condition? It's a nightmare. What is the speed? Speed is, tabulation is pretty fast because it's just for loop. You just do it. And then memoization is kind of slow. Why? Because you have to create a new function that will create a new call stack. Then that call stack will be put up in the stack. Then once the call gets over, then the stack has to be cleared. It is slow, and it takes more time. This is one very good difference that they have mentioned here, and also I would like to talk about it. That is sub-problem solving. So what here he meant is, if you're using a tabulation approach, and if you're doing an optimization problem, let's go this way. So when you're in this problem, right, if you're using a top-down approach, you know that you really don't need to. So when you're trying to compute CD, okay, what he meant was, or what the idea here is, if you're trying to do in top-down approach, because it's an optimization problems, you really don't need to consider all the sub-problems, right? You only need to consider, because there is always a strategy for you to eliminate some problems based on a condition, right? Like for example here, once you found out the maximum path from B to C, you really don't need to worry about this B, E, and EC. you just need to worry about BC. Similarly, once you have found out the path, the maximum path from C to D, you just need to worry about that only one path. You don't need to really consider these paths in subsequent computation, because the first time when you compute, you might have to consider all the paths. But the second time when you're doing it, you really don't need to do it. You just need to store this value, and that particular subproblem is kind of avoided, right? You're not doing it again and again and again. But not only that, in top-down approach or in recursive code, because you have the flexibility to write a recursive code, you can always put an if condition somewhere in the code, and you can eliminate a major chunk of subproblems without actually evaluating based on one single check. Like example, if my size is greater than 1000, then go to the right. If my size is less than 1000, then go to the left. That one if condition is good enough, and you can eliminate a major chunk of subproblems in top-down approach. But in case of tabulation, what did I say in tabulation is, all the combinations in the memory should be stored, and then you retrieve the maximum value. So here you cannot eliminate the subproblems, which you really don't need to, which you can always do it. But in case of tabulation, you have to put each and everything in the table, and then you retrieve the maximum value. So you see, inherently there is, how much, I mean, we are like all the subproblems should be solved at least once. And a bottom-up, bottom-up dynamic programming algorithm usually outperforms a top-down memoized algorithm by constant factor. So basically what they're trying to tell here is, if it is a top-down or memoization with hash map, then you really don't need to solve all the subproblems. You can always eliminate a bunch of subproblems. But in case of tabulation, that you need to fill the table. You cannot have a sparse matrix and you cannot retrieve it. That is not the way the tabulation works. You need to fill the table, and then you get the value. So that is tabulation, right? So all the subproblems should be touched and should be computed. But in case of memoization, that is not required. You can always eliminate a chunk of it based on your if and else condition. Like for example, if you're doing some sort of, if you're doing some sort of trying to find out the most, what do you call, like if you want to get all the positions in the even locations, right? Or if you want to get all the positions which are in odd locations, then what you do, you can just check, okay, if this index is divisible by 2, then compute it. Otherwise you don't compute it. That if else condition cannot be put in my tabulation. I need to do all the computation. That is one problem with tabulation. Table entries. So in table version, all the entries are filled one by one. It is obvious you need to fill the entire array, but in memoization, you only persist those values which you think will be useful in the future. That's why the lookup, also known as the lookup table, all the entries are not really required. Only those entries are required which you think you might be using in the future. That's how you would put the values in your map or in your lookup table. But unlike in tabulation, you actually fill the entire table and then you retrieve it. So the only advantage that I see is it's a speed. And the only disadvantage with my recursion is it's kind of slow, but you can always improvise it by writing an efficient recursive code, by using an efficient lookup table and trying to, there are a lot of small nitty-gritty, tactics that developers use to speed up their programming by using static variables instead of, creating the variables runtime, or instead of having some constants. You can always save some data. You can always save some speed. So that is the advantage with memoization. But overall, if you do a time comparison, memoization is kind of a slow, it is recursion. You have to create, the call stack space goes up and down, but tabulation is kind of faster, but it comes up with a baggage of its own problem. So most of the problems in dynamic programming, whenever we see, the problems are always implemented using recursion with memoization as hash map. But that doesn't mean that is the only way. You can always solve with tabulation also. And it depends on the developer. At the end of the day, it finally depends on the developer who's actually writing the code. What he feels comfortable, he or she, they will go with that approach. But this is just a generic comparison between both the strategies. And this is about dynamic programming, tabulation versus memoization. If you guys have any question at this point, please ask me, or because this is just a very it's just a very topic, very kind of a topic that is not much frequently discussed. Even in a work environment, we don't talk much about dynamic programming. It is only discussed in an interview context, or mostly by algorithmic experts who are trying to build up some really cool algorithms. Only in those contexts we talk about dynamic programming, but not in any other regular day-to-day work. So if you guys have any question, feel free to ask me. If you want any resources or where you can find dynamic programming easy to understand, or I can just help you out, guys. Otherwise, we can end the session.
So, Sandeep, this is Suva. I just have a couple of questions. Question number one is, was this your last slide, or do you have any additional slides as well?
No, this is my last slide.
Okay, okay, great. So just wanted to know from a pacing perspective, I think you have paced yourself beautifully, so that's great. But I do have a slightly longer second question.
Sure, go ahead.
So as others think about their questions, my question is from a user usability perspective, right? So you gave us a couple of examples, the step problem, and I think last time we discussed about factorial and also the Fibonacci series probably. So from an interview perspective, when somebody gets a problem wherein potentially they could approach either the tabulation approach or memoization, how should they approach such problems? At what point in time would you know that, hey, you know what, this is not a cut and paste recursion problem. Maybe I need to think from a dynamic programming perspective. Any tips? Because many of the people on the call right now.
Yeah, that's a very good question. So that's a fantastic question, actually. So the question here is, how do I know that I need to use a dynamic programming strategy, right? That is the question, right?
Yes, yes.
Okay, so you need to, like, if there's a problem that is given, you have to find out the, can I use my Notepad++ because I want to write, because I'm getting some ideas. I don't have a slide. I'll just stop this share and I'll just create, just give me 1 minute.
Yeah, sure, please. In the meantime, the rest of the folks on the call, thank you again for patiently, being on the call. We truly appreciate that. Please do ask your questions. You'll have to unmute yourself. Yeah, go ahead.
Yeah, you guys are seeing my screen, right? So how do you find whether it's a DP, it's a, when to use dynamic programming or when not to use dynamic programming, right? So most of the questions with regards to dynamic programming, it's about, you have to find there's some sort of optimization that is being asked. Okay. And so these are I'm talking at a very abstract level, just forget about the problems. But if these things are, if the problem has these themes to it, these ideas, then it somehow, somewhere it can be a potential candidate for a DP problem. So if the theme of the problem is to do some sort of optimization, okay? Optimization. If the theme of the problem involves some sort of optimization. Second thing, if it has optimization, so the moment the optimization bell, if the problem has some sort of optimization, what the common sense approach is to take the greedy approach, right? You just take what is available immediate. You check the local, you do with a greedy approach first. You just mentally think greedily. This is how I do all my problem solving. If there's optimization, I first go with a brute force, also known as brute force approach, which is greedy in nature. Okay, and then the problem will fail for a test case. will fail. Why? Because you need to consider the future options. So now, because you want to do an optimization and you're just looking at the variables that is available to you and you're moving forward, and that is not giving the right solution, and the problem will fail. So if you have to consider all the options, if you have to look at all possible options, if you have to look at all possible options, then this can be a candidate for DP. So what I'm saying is, if a problem, like what is an optimization problem? There is one problem, you know, let me share you something else here. Stop share. Hold on. Share screen. So this is a famous computer science program problem, you know, because these are 3 points, okay, and a robot is trying to so basically the robot is trying to want to connect all the paths here. The robot has given, so these are the points, and the robot is like you are in a robotic company and there is a chip and these are the points, and the robot has to solder all these points in the most optimized way. So as a robot, I can always do like this, right? If I'm a robot, one option would be I can solder these two here, and I can solder these two here. I can solder these two. I can solder this way, right? Because I need to connect all of the points as a robot, but I want to solder, or I want to connect all this point in the best optimized way. So it should ring a bell. Okay, here they're talking about optimization. So that is one. So this can be a candidate for dynamic programming. Now try to do the same problem. Now when it comes to optimization, now first go with a greedy approach. Don't even go with dynamic approach. Go with the greedy approach. If this is solving your problem or not. If this solves your problem when you approach greedily, then that's fine. Then then it's an optimization and greedy strategy work. And how do you know whether it will work or not? Is you play with the problem with a test case. Every problem has a test case. So you play with the problem. Generally, the interviewer, given a problem, he will give you 2 or 3 test cases. And you see whether by using greedy strategy, whether the test cases are passing or not. If it is passing, then don't even think about greedy. Just go with the best approach and just move forward. Just take the greedy options and you move forward. But if it is not, the greedy strategy is not working, and you have to think, sometimes you have to think greedily, sometimes you have to think non-greedily. So if the solution involves these 2 combinations, where sometimes you have to think a greedy, sometimes you're not thinking greedy, then only you're getting the solution, then that means you have to evaluate all the options. And if you're evaluating all the options, then you go for, then when you're doing that sort of evaluation of all options, you will write some sort of recursion code, and that's where it will become a candidate for dynamic programming. Does that answer your question, Suva?
Yes, it does. Thank you, and thank you for that long.
Do you still have any question? Because generally this is how I learned. This is from my own personal experience when I was solving problems, especially with regards to any sort of optimization problems, or sometimes not necessarily optimization. Sometimes a problem might ask like this, you know, the problem statement could be like this: find all possible. The problem itself will tell you find all possible. So that means when you're trying to do all possible, then you would go for some sort of recursion, right? Again, it depends on the developer, because some developers might say that I don't want to use any recursion at all. Then yeah, fine, you can go with some strategy. But if the problem is asking you to find all possible combination, and you want to, then you can always use some sort of recursion. And if you're using recursion, and if you think that the problem has some sort of recomputation that is taking place again and again, then memoization can kick in, and that becomes a candidate for dynamic programming.
Wonderful. Sandeep, thank you. We still have quite a few folks on the bridge. We've hit 5:30. Folks, please ask your question for Sandeep.
My recommendation for everybody, if you're trying to learn dynamic programming, start with top-down approach. The bottom-up approach is like, I mean, people, like, to be really honest, the interviewer will only check whether you know bottom-up approach or not. The whole idea of so even in my slide covering, I didn't spend much time on bottom-up approach, because the whole idea of bottom-up approach is to check whether you know bottom-up approach or not, and whether you know how to, given a state transition equation or the mathematical equation which has a recursive nature to it, can you put it in the form of a matrix, and can you fill up that matrix? So you don't need to write code. Sometimes the interviewer asks, for example, this problem, right, where I have given f of n equal to, so if this could be another recursion, right, f of n minus 1 plus 1. So given this problem, the interviewer actually wants you to write a recursive code. They don't want you to write a simple for loop and get it done. They want you to write a recursive code. But after you have written the recursive code, they will check, can you speed up this? So you will put map. Then he will say, can you speed up even more further? Then you say, okay, I can go with a tabulation approach, and you really don't need to write code for it. All you have to do is you just need to just create a matrix like this, and tell him what is my, so you tell him these are my row values here. So tell him these are my values here, and these are the values that I have here like this. And what you do is you start filling it from the, you start filling it from the bottom, or you start filling it from the break condition, also known as the bottom. And accordingly, you just go ahead and fill up the matrix and tell him that, hey, I can use this sort of tabulation and get it done. And this should be good enough. But most of the interviewers, when they are testing you, they'll always look at your ability to think recursively, apply to the problem, and can you use memoization technique to even reduce the execution speed. That is where they are checking your programming abilities. Any more questions, guys? I can wait for 2-3 more minutes, and if nobody has any question, then we can end the session here, or any question, that's fine, I can answer.
Sandeep, I have a question on the space complexity here. So it will be since I'm using recursive plus memorization, it will be the double, right? Like order of n square would be the space complexity with the DP, right?
No. You're saying order of n square for space complexity?
Yeah. So so basically my question is like, so we are doubling the space right here, like, because I'll be using
No. Yeah, but which approach you're talking about, top down or bottom up?
In either way, okay. So in either way, we will be like, since we are storing the.
Okay, I got your question.
Okay.
You are correct in bottom-up approach, where in bottom-up approach, based on the number of variables. So here, what is my space complexity is O of n, right?
Yeah, correct.
Okay. But you have an equation like this, f of x comma y f of x plus 1 plus 1, if this is some equation like this, plus f of x plus 2, if you have something like this, then the space complexity is number of rows into number of columns, the matrix size, right? So this is correct, right? Till here you're with me, right?
Yeah, that's correct.
But now in case of recursion, it's very tricky. Why it is tricky? Because let me open this, let me share the slides here. So recursion, you have a call stack. In a recursion, when you're doing a space complexity, at any point of time, the maximum space that it takes is the maximum number of call stacks that you have. At any given point, you will not have both F. So when the computer is executing, or let's talk about Java, when the JVM is executing, it executes them in the fashion of a call stack. Okay. So when you talk about space complexity, in case of recursion, first you need to know what is your length of your call stack here, multiplied by the space taken in each call stack, plus the map space in itself. So in recursion, you cannot say that the space is n square or number of rows into column or O of n. In recursion, the space complexity is generally based on the number of call stacks. And in this particular case, the number of call stacks is nothing but the maximum length of the tree that you have here into the space taken by each function. That is how you calculate, plus the map itself. That is how you calculate the space complexity of a recursive code. So please always remember that any recursion, the moment you see a recursion, the space complexity is given by the length of the maximum length of the call stack tree. That is how you write the recursion. That is how you compute the space complexity. And this could be lesser or greater than the tabulation space based on your call maximum call stack length and per call function call how much memory you're taking plus the lookup table itself. So you need to compute, and there is a strategy. I think I've already discussed it in the recursion video where I said how given a recursion code, how do you calculate the space complexity. Does that answer your question?
Yes, Sandeep, maybe I'll go through the
yeah,
previous
please read.
video.
So please read that finding the space complexity for a recursive code. I think somebody posted something in the chat window. Any other questions? And there is, and another way is also if you're doing a recursive code, there is the question that they ask is what is a time complexity? And time complexity is, I have also discussed that in my previous recursion code, but for just for information, I will talk about the time complexity here. So the time complexity for this code would be number of children. It will be if you have m children, m into the number of times the recursion code is being called. So if I have m children, m into f of n minus 1, something like that, for example. So basically what I'm saying is, okay, let me share my notepad++. Share screen here. Or actually, so basically recursion, right? So recursion actually is like a tree. something of this sort, okay? So the way you compute the time complexity for recursive code is, so these are very important. It's very, very important, especially the space complexity, time complexity. You guys need to know it, and that is not subject of this discussion, but I'm just giving a small information so that if you guys are doing it by yourself, it will be useful. So what you need to do is first calculate the branching factor. So here, assuming the branching factor is 3 into f of n, and this is and how many times this will happen based on the branching factor is 3. That will take place 3 times of f of n, and again this will take, this particular thing will again do 3 times. Let's assume like this. It's a very important concept here, and that will again be so this will again be 3 into 3 times of f of n. So that will be like 3 power k into f of n, something of this sort. So this is not the complete explanation, but what I'm saying is basically you have to take the branching factor and the, you know, how much computation you're doing multiplied, again you have to do with the branching factor, because this f of n will again take place 3, like initially it is 3 times of f of n, right? But what is this f of n again is 3 into 3 of f of n minus 1. This will again sum up to 3 into 3 into f of n minus 2. You see, and eventually it will hit at some breaking condition. So that will be like 3 power k, where k is the length of the call stack, where 3 is the length of the call stack. Sorry, k is the length of the call stack, 3 is a branching factor, and then into every function, every call stack, per call stack work, per function call work, something like this. This is very theoretical. This is not complete. This is, I'm just giving you an idea. How do you need to approach if you have to calculate space complexity and time complexity, and interviews, they will check your space complexity and time complexity. And if you guys have difficulty in computing the space and time complexity, there is a theorem called Master's theorem. Please read it or by heart it, and the Master theorem has a formula. You can just put that, plug in that formula, and you can directly get your time complexity. Okay, please do that. Or if you don't want to memorize anything, you can intuitively derive something like this. Any more questions? What sort of practical? I've already mentioned, right? Any sort of optimization, or if you want to find out all possible combination, mostly it has to do with optimization. Always it has to do with some sort of optimization, or if you have to find out practical application. Oh, sorry, if you want to find out possible combinations. Now, what are the practical applications? We have already discussed one practical application, right? You are doing a city survey, and you're doing a place survey, and you want to find out the maximum. Google Maps could be one. If you want to find out the longest distance or the shortest distance, or especially in traffic, you know, now when traffic kicks in, if you want to do a shortest path without traffic, then you can go with greedy, right? Whatever is short, you can do it. But with traffic, then the whole dynamics get changed. Then with traffic, Google Maps, they cannot use greedy strategy, because even though the path is short, the traffic is so much, the cost of the path will get exponentially, increased. So in that kind of variable condition, when the factors are not same, then you have to consider all possible aspects and do a dynamic programming. So that could be one practical application. Any more questions? Okay, if you guys don't have any question, I hope I have added some value to you guys with regards to dynamic programming. I did my best because dynamic programming is a very tough concept. I tried to make it as simple as possible. And I didn't spend much time on tabulation because it's really not that, I mean, once you get the top down with the hash map memoization, that is more than enough. That is like you have done with 80% of dynamic programming. The last 20% is bottom up. It is whether you really know about it or not. That's all about the interviewer cares about. Even when you're thinking in problems, we always think in top-down approach. Nobody would think in matrix, right? Unless and until we are a bot, we can think in that very dry way of thinking. We always think in intuitive way and in recursion. So top-down approach is the most important part, and that's why I spend the meat of the discussion was with the top-down approach. You guys have any other question right now? If you don't have, then we can end the session.
All right. There seems to be no more questions, Sandeep. I know we went a little bit over, but thank you again for your time. And thank you folks for staying the extra 15, 20 minutes. On behalf of all of us here at BayOne Solutions, all the attendees, we greatly appreciate your participation and in giving back to the community, Sandeep. We actually eagerly look forward to having you back again as a guest speaker sometime. Okay, so thank you again for your time, and thanks everybody for joining. Have a great night and see you all next week on Tuesday.
Okay, bye guys. Thank you, Suva, for giving me an opportunity. It was really nice. Actually, it was a very good brush up for myself as well, because I need to, now it's like when I was preparing the concepts, like I was like, I have to think through the entire subject as well. So it was a good learning experience for me as well. Thank you very much, guys, and have a nice day. Bye-bye.
Wonderful. Thank you.